So here we are. We're going to talk about diffraction. So we said that this was the change in direction of energy transfer of a wave as it passes around an obstruction or boundary. Some people will also describe diffraction as the spreading of a wave around a boundary. Both are totally fine in terms of definition. So let's just draw what we saw. So if I have my boundary there, okay, let's just color that in just so we know that's a boundary. And I had my straight waves coming in, okay, boom, right, maybe another wavefront there. So what did I see? Well, hopefully what we saw here is that there was a segment of the wave that continued through as if nothing was happening to it. And then what happened here is that we had some on the edges of that, some curvature, right? And the degree to which that curvature happened would be the degree of diffraction. So there we go. That's the picture of diffraction. Now, if some of you are sitting there to yourself, well, actually, let's just draw a couple of rays in first. So here's a ray. Here, you can see that that ray is bending. That's the change in direction of energy transfer we're talking about, because the ray has to remain perpendicular to the direction of energy transfer. Perpendicular to the direction of energy transfer. Now, if some of you are sitting there thinking, my God, that looks kind of familiar. If I turn it this way, it might look a little bit more familiar. And if you're thinking the Wi-Fi symbol, you're right. The Wi-Fi symbol is a picture of diffraction because a lot of our Wi-Fi works by diffraction. If you think about where your transmitter is, that transmitter is sending signals all throughout your house or your apartment, and there's walls in the way. And those walls could block the signal, but instead of blocking the signal, what's happening is they're getting to openings in the walls, like doors or windows, and they're bending around into that space, which is how one or two nodes within a space can cover an entire area. But if you have a lot of walls and weird shapes in your house, that's why you might need multiple nodes, because even with all that bending, it may not still be able to get around to everything that you need. Anyway, diffraction. The bending of the wave as it passes around a boundary. So we saw that there were two factors that affected the degree of diffraction. Now, I want to show another diffraction picture before we get into the factors that affect diffraction. If this is my boundary, say, and here's my straight wave coming in, if I just have the one boundary there, I just get this section remains straight because nothing's happening to it, and there you go. You have your diffraction happening here. Okay, so it's important to note that during diffraction, once again, the speed of the wave does not change because the medium doesn't. The frequency of the wave does not change because the source doesn't. Therefore, the wavelength does not change because neither the speed nor the frequency changed. We saw a diminishment in the intensity or amplitude of the wave because that wave had to spread out over more area afterwards, right? So those are some of the basics of diffraction. Now, in terms of factors that affect diffraction, let's flip the picture again so we don't get used to looking at it in the same way. If I had same opening there, right? So I'm going to draw two pictures side by side for comparison. Let's say that the slit width, and we'll call that a slit width W, is identical between these two, right? And I had straight waves coming into that boundary afterwards, if let's say that this had a smaller wavelength and this had a nice large wavelength, here we would see a greater degree of curvature, whereas here we would just see, okay, just a little bit of curvature on the edges, okay? So you may ask, well, why would longer wavelength equal more diffraction? Well, very simply, we have the wave bending, right, and spreading. When the waves are closer together, there's not as much space to spread. It's a little bit more complicated than that in truth, but that's the basics of it. So longer wavelength means more diffraction. How do I get a longer wavelength? Well, I can have longer wavelength by doing a smaller frequency, or I can do that by having a faster speed. But longer wavelength means more diffraction. Okay? Then if I want to compare sizes of opening, if I have a really, really narrow opening versus a really wide opening. So here I'm varying W. Okay? So here W is different, but the wavelength is the same. And so here I'm going to get almost perfectly circular waves. The smaller W is, the more the waves look like it's just a point here. In fact, if this was really close together, it'd be almost the same thing as tapping directly at that point. Whereas here, what we're getting is just a slight curvature at the end. I don't mean to suggest here that the wavelength is changing. It's just a little hard to draw, okay? And so here we would say, right, smaller W, more diffraction. So if I wanted the most amount of diffraction, what am I doing? I'm going to have a narrow opening and I'm going to have a long wavelength, right? And so that is the basics of diffraction.